So thank you very much for joining this modeling forum talk. And today's speaker is Dr. Reinhard Hinkelmann, and I'm very pleased to say that Ilhan, who is in Berkeley lab, he worked with Dr. Hinkelmann in his PhD. So I will let Ilhan introduce Dr. Hinkelmann, and then you can take it away. Thank you.
Okay, thank you, Dipankar. It's my pleasure to introduce Professor Hinkelmann. He's an established scientist and has many accomplishments, but to keep this introduction short, I will just count the most recent ones. So he is leading the chair of water resources management and modeling of hydrosystems at Technische Universität Berlin. And he is the speaker of the research training group Urban Water Interfaces, which is a large research training group funded by the German Research Foundation. It goes for 9 years, and it comprises 3 generations of 13 PhD students. And his research interests are on robust numerical methods for flow modeling, and he also is interested in machine learning methods with application to urban and environmental flows. And with that, I'll silence myself. And Philip, if you want to share your screen and start, that would be wonderful.
Yeah, thank you very much, Dipankar and Ilan, for this very nice introduction. So, and I would like to share my screen. So, give me. Okay, I hope you can see the screen. Is everything fine? Maybe someone can give me feedback. Yeah, okay. Yeah, I would like to mention that it's really a great pleasure to be invited to this famous Berkeley lab, and it's a pleasure and an honor. And what I mentioned also in the small talk before, I hope there will be any opportunity also in the future to visit your lab in person. And of course, it's a pleasure to meet Ilan again. It was introduced, we collaborated over many years. I'm glad that he could join your institution and lab and continue his career. And of course, it's also interesting to come in contact with other persons and maybe to get or establish new contacts. So before I start with the scientific presentation, please allow me to give you a short introduction to TU Berlin and my chair, and also I think I have 2 slides prepared for this research training group. Yeah, let's say as an add-on to the presentation. So the chair is at the Technische Universität in Berlin. Probably many of you know Berlin is the capital of Germany, and we have several universities in Berlin, and the Technische Universität, of course, has a focus on engineering, technical things, and so on. So we have different campi. We have a main campus. So my chair is located on a campus in another quarter. This campus is called Wedding. So, and some ideas on TU Berlin, we have 35,000 students in average. We have 350 professors. So the ratio is 1 to 100. If you look in the US and in the UK, probably the number is much better there. Yeah, nevertheless, it also works in Germany. So we have 7 faculties, and from the organization, 7 faculties. My chair belongs to faculty 6, Planning, Building, Environment. Within the faculties, we have institutes. In our faculty, we have 8, the architecture, geosciences, landscape engineering, and others. So, and also civil engineering. And within the institutes, we have the chairs. So in that sense, you can say the chairs are the smallest units. And my chair is one of the 13 chairs of this institute. There is another chair in the water field of Professor Bayenbruch, who does urban water management, and we are closely collaborating. I may also add, this is not on the slides, Berlin has been successful within the excellence strategy of the federal government, and with that since 1.5 years, there is a joint activity of Berlin. There is the Berlin University Alliance, where these 4 universities are collaborating in various fields, and we are also glad that we can participate in one of the bigger research activities to start at the beginning of next year, which is called CLIVA, Climate Impacts on Berlin and the local surroundings and regional surroundings of Berlin. Okay, so my chair is giving courses in fluid mechanics and hydraulic engineering, in hydrology and water resources management, and in modeling of hydro and environmental systems. And the courses are given in the bachelor and master in civil engineering in German and in English, and also in environmental science and technology. And also we have an outer campus in Egypt where we offer a program in water engineering. To add on that what Ilan mentioned, the research fields where we and my group has worked within the last, let's say, 15 years is related to modeling of flow and transport processes in surface waters. Among them, of course, the robust numerical methods, where I'm specifically interested what Ilan mentioned. Also modeling in the subsurface and model development and hydroinformatics. So, and among the research activities, this research training group has already been mentioned. Allow me a few comments on making a PhD in Germany, because it differs a bit from how it is running in the US and many other countries. So in Germany, to make a PhD within a structured program is not that common. I would say much less than 50% of the students do a PhD in such a program. So they make a PhD within, let's say, within a project, or they are funded by the university, by basic funding, as was the case, for example, for Ilhan, or they have a scholarship, as is the case for Jia Heng, who is connected from Loughborough. So, and we do have PhD programs, but let's say they are more, they provide you some framework, possibly a little financial support, but they don't have from the content a clear focus. When they exist, they have more a broader focus to say we have a PhD program, let's say in the water field, for example. So, and also specifically looking on Berlin, there have been a few, they have not been that successful, to tell the truth. And yeah, and making a PhD in Germany generally takes a relatively long time. 4 to 5 years is quite common, and I think it's faster in many other countries in the world. On the other hand, these kind of research training groups do exist in Germany. They are funded by the Deutsche Forschungsgemeinschaft. In that sense, they are, well, one can say, highly ranked. If you make a PhD there, you put it in your CV, and it's good for your CV. And they can also be done on an international level. And what differs from the normal programs I mentioned earlier is that they have a strong scientific focus together with the qualification concept and providing some structural framework. And the most important thing is that they are third-party funded. That means you have to write let's say a proposal, and it's quite competitive. Maybe 20% of the proposals are funded at the end. On the other end, when you are successful, you get around €1 million per year, and it is in a similar range as $1 million per year. So as Ilan mentioned, it is running over 9 years. There is an interim evaluation. We passed that some time ago to get the full funding, and 3 cohorts of doctoral students can be educated. So we can say they already exist at least 20 years, and they have been quite successful with regard to the scientific output, and also with regard to a reduction of the period of completion of the PhD. Okay, let's say some information on that urban water interfaces. Why are they important? Because let's say they play a key role in the urban water cycle. They connect a large number of compartments and subsystems, and they have a considerable impact on the overall system behavior. So, and we have a very broad view on interfaces. There are interfaces in natural systems. I will comment in the presentation between groundwater and surface water. There are interfaces in technical systems like a sewer system between the wastewater and the air, or there are interfaces between natural and technical systems like bank filtration, which is also quite common in Berlin. So, and in addition to that, we have identified 4 areas where we do very intensive collaboration. We call these field common topics fields. And with regard to the qualification, let's say we want to link engineers and natural scientists. I forgot to mention that the research training group is a close collaboration of the Technische Universität Berlin together with the IGB. IGB is the Leibniz Institute for Freshwater Ecology and Inland Fisheries. This is a leading institution for freshwater ecology, for lakes and so on in Germany, and it's also internationally renowned in the world. So, and we want to bring them to a new quality of interdisciplinary knowledge with a strong international component, and that within a structured framework. So we have developed specific courses. We have developed 3 new courses to bring engineers and natural scientists, to try to bring them on a similar level of knowledge. We carry out summer schools. Of course, in the last times, all the things went more into the digital space. We're offering internships. There was also last year, we planned maybe that one student will come to your lab, but through Corona, it was not possible. So we are inviting visiting researchers. We have a board of supervisors for each PhD student. And we also have a specific gender concept to support PhD students who get babies and so on. Okay, this for the short introduction to give you some ideas. And now I'm coming to the scientific presentation. Okay, again, I would like to check whether everything is visible with the slides.
Yes, it looks good.
It looks good. Yeah, thank you very much. So today I would like to talk with you about an integrated Navier-Stokes solver. Of course, with the help of the solver, we can improve the process understanding in the interaction space surface water, groundwater. So, and the major part of this presentation, so all the work comes from this research training group, and the major part of the presentation is part of the PhD of Tabea Bröker. So she finished last year, and there are also contributions from Vahid Gollo. Let's say he comes into the final stage of his PhD, and I have the pleasure to present the results of these PhD students. So we see here on the left a nice figure, which, let's say, has been something like a very specific figure for this research training group. I would like to add, if you look to the bottom, that this figure has been developed by Ilhan and me a couple of years ago. So, and we have reused it many times. So Ilhan, the effort was, of course, quite good to be done. It's really a nice figure. So within the presentation, I will give you a short motivation. Then I will introduce the methods and we used and extended within the open source simulator OpenFOAM. And then there will be 4 application cases. 3 are related to flow and transport processes at the interface groundwater surface water. There is a 4th case where we consider another interface between free water and porous medium flow. And this is let's say a burrow which has been digged by something like an earthworm. So, and at the end, some conclusions and an outlook on further work. Okay, maybe first the hyporheic zone. probably you are all aware that the loads on water systems are increasing, more specifically even on urban water systems, they are increasing, and we have to expect climate change and other changes that will increase the stress on these systems. The hyporheic zone, let's say, connects the surface water with the groundwater, and a lot of biogeochemical reactions do take place there. So we can, on the one hand, we try to protect this zone. On the other hand, we may want to engineer this zone to make advantage of the zone, because the zone has some possibilities, let's say, to remove or to retain contaminants. So, and if we want to go there into the details, of course, it's good to know how the processes do occur there, how are the flow and transport processes in these areas. So, and we improved our process knowledge within the last couple of years there. Okay, we can do that, of course, with lab experiments. Other colleagues in this research training group did lab experiments and field experiments. Our focus was on modeling. So, of course, the time scales are quite different between surface water and groundwater. In surface water, we have a flow velocity is a meter per second, while in the groundwater, it's a meter per day. So quite different time scales. We have to bring them together. And the quite common approach, and probably also applied a lot in your group, is that we have a separate model for the surface water flow and for the groundwater flow, and you do some coupling. So, and the question is, for some questions, a simple coupling might be sufficient, no question, but there are also questions where the interaction between the two systems play a very important role, and there, let's say, more advanced methods need to be taken into account, which also can account for feedback effects, for example. Yeah, if we consider a bit the state of the art, so different approaches to exist, the coupled approaches, there is a one domain approach already, let's say, a couple of decades old. There is a classical two-domain approach of Beavers and Josephs, where they introduce a specific parameter to account for the jump in the shear stress at the interface. So this is generally determined, this coefficient, by some calibration. And what is done in many cases is a one-way coupling, again, without taking in through one-way coupling through the pressure and without taking into account feedback effects. Okay, yeah, and of course, what also might become interesting when the river sediment or the porous medium is a bit coarser, then let's say also the Reynolds numbers or the flow within the transitional zone may become much higher than Reynolds number 1, and then we are out of the range of the Darcy law. So therefore, the question is: are there other ways to take into account the processes that occur around this interface, including the feedback effects? Are there other approaches how to do that? Unfortunately, the answer is yes. And persons already did some work on that, and we could use that work and extend that work. If we formulate a modified version of the Navier-Stokes equation, we can apply the same model concept for the porous medium and for the free flow. Of course, we will see soon, we introduce a porosity. This is 1 in the free water, and of course, it's 20–30% in the porous medium. And let's say another term, a specific, let's say, resistance term will be introduced, I'll show you soon. Probably most of you are aware that, let's say we formulate balance equations, mass balance equation, momentum balance equation, in this case, the Navier-Stokes equations. So then we end up with a system of PDEs, partial differential equations, coupled, in this case also nonlinear. We do some discretization. OpenFOAM uses the finite volume method in space and finite different techniques in time. And then we end up with algebraic systems of equations, and we need some solvers, and there are a couple of techniques of iterative solvers where we use on the one hand to solve the systems of equations, and also, let's say, for the Navier-Stokes equations, important to couple the pressure equation also with the momentum equations. So, and what has been mentioned earlier, we used and extended open solvers provided by OpenFOAM. So we have, on the one hand, we started first only to model the flow in the river and excluding the sediment, though the sediment was the rigid boundary. So, and there a solver was available called Interfoam. This uses a volume of fluid method. We used it also for two phases. I come back to the two phases quite soon. And to capture the interface between the surface water or the water and the air, an interface capturing approach is used. So this method has been extended by a transport equation by Navier-Stokes. And then, more importantly, we where the free flow as well as the porous medium flow is included. This solver is called the porous inter. It's based on Interfoam and was available and has been extended. In the second and fourth application, we applied that. And in the third case, we extended the solver also by a transport equation. Okay, some ideas, or let's say the balance equations for the two-phase flow solver. Why do we need two phases? We need two phases when we simulate the flow, for example, over ripples and dunes in a riverbed, and the water level is only a few decimeters high. Then to track the free surface, one good possibility is to use let's say to use two phases, the air phase. On the other hand, only to have a good, let's say, a good free surface. And what we also found out, especially when the water level is not that high, between the dunes and the ripples, complex eddies do occur. I will show you a couple of them soon. And then the pressure distribution, there is no more hydrostatic. So, and therefore we would get much poorer results with a shallow water model. So therefore we use the, let's say a Navier-Stokes solver there also to fully resolve the momentum in the vertical direction. So therefore, for smaller water depths in the range of a couple of decimeters, two-phase flow is quite necessary, and this occurs in many small rivers and creeks. On the other hand, let's say if we have a 10-meter water column, then it doesn't matter whether we have one or two phases. Okay, the equations that are included are quite classically, it's the conservation of mass and momentum. Following this two-phase flow approach, we introduce a variable alpha. Give me a second to include the laser pointer. Yeah, so we introduce a variable alpha, which is 0 when we are in the air, and which is 1 when we are in water. And of course, in between also values in between are possible. So in each cell, it is considered how much of the cell is filled with water, how much with air, and from that the alpha value is determined. So therefore the fluid properties, the density, the viscosity depend on this alpha parameter. And for the viscosity, we include on the one hand the physical viscosity, and on the other hand we can add the turbulent viscosity using different turbulence models. I have a slide on that soon. And for this two-phase flow approach, we also need to add an interface convection equation for this parameter alpha. So what I mentioned, we added a classical transport equation. You see here the transport equation, advection, diffusion, and there is also the turbulent Schmidt number, which relates turbulent diffusion to turbulent viscosity. Okay, a bit more interesting is this integral two-phase solver, which accounts for the flow in the porous medium and in the free flow. So, and there we have to add first the porosity, so shown here in red. So the porosity is added to each term of the mass and momentum and interface convection equation. The other things remain more or less similar. And there is a further term added to the momentum equation. And this is, let's say a resistance term, which accounts for different effects we will see soon. So here is the resistance term in detail, and maybe to comment on how is the porous medium taken into account in this extended version of the Navier-Stokes equation. It's taken into account by a porosity and by a characteristic diameter. So there is no permeability or hydraulic conductivity. This is not taken into account. These two parameters describe the porous medium. Of course, when we know these parameters, we also have an idea on how big the hydraulic conductivity or permeability can be. So, and these terms, the first term accounts for the friction of the fluid with the porous medium. Let's say an approach from ergon has been implemented. And the second term accounts for an increase in the effective mass, and it also accounts for recirculation zones, and another experimental approach or results from Van Gent are implemented there. So this solver is, this resistance term behaves quite good for coarse material when the, let's say when the dP is in the range of centimeter or millimeter. If it goes much beyond a millimeter, then the CPU time is tremendously increasing, and then it's no more that recommended. Okay, we also added a transport equation on that. Nothing specific compared to the previous part. And with regard to the turbulence, so fortunately in open form many models are available, like the standard K epsilon, the K omega, and the combination of both is K omega SST. It's sometimes we made good experience with that. And for some cases, we even used the LES method, and the LES method, of course, resolves much more of the eddy structures. Let's say the causal eddies are directly resolved by the grids, and we only need a model for the very fine eddies, which are below the grid size. On the other hand, the systems we investigated, the factor, there is the CPU time increases by at least by a factor of 10 when we switch from K omega SST to large eddies. So therefore, we carefully have to check whether this is really needed. We have to generate a mesh. There are some possibilities within OpenFOAM, but we can also add external mesh generators, and then we have to set, of course, on the boundary conditions. And I may mention the system we will see soon. We have an inlet and an outlet, and then we have an upper wall and a lower wall. Different kind of velocities are set for the velocity, the pressure, the concentration. In the principle, they are of Dirichlet or Neumann type. I would like to add, if we compare this CFD simulations, let's say with shallow water simulations, it's a bit more tricky to come to stable results. For the CFD model, you need to have a good combination of robust boundary conditions, a fine mesh, and the suitable turbulence model. And yeah, let's say it takes some more time when compared to shallow water flow modeling. Okay, that brings me to the first application, flow and tracer transport at a rippled streambed. And before we went, let's say to natural-like systems, we wanted to test our the solver. And, we did that with several cases. I'm showing you here one case. There were experiments carried out by a person, Fehlmann, and he investigated a system where ripples or dunes have been idealized by triangles. So, and their data were available, and we could compare our numerical results with these experimental results. So, and what we can see here is the pressure increase, the pressure or the pressure difference of the real pressure minus the hydrostatic pressure along the line of one of the ripples or dunes. So, and the full line show the simulations, and then the dotted line show the measurements. Except the area here, the agreement was quite good. And we have to add that, so the peak here comes from the result directly on the tap of the triangle, and no measurement device has been there. So except this part, the agreement was suitable, and we also, let's say, had an idea that model and numerical results or experimental and modeling results agreed to a large extent quite good. Okay, and then to add the transport equation, we did, let's say, standard cases. There are 1- and 2-dimensional analytical solution for constant and pulse injections, and we checked our model with that, and the agreements were quite good, so that we thought we now can also apply the solver to other cases. So in the case what Tabea investigated very systematically is shown here. So we have a system 1 meter high, and then let's say 50% or 50 centimeter water, 50 centimeter air, and we have an inflow area so that the flow is developing, and it's fully developed when it's reaching the ripples here, and then some outflow area also to have good conditions on the outflow side with the outflow boundary. And then she made many investigations varying the ripple height. So the ripple height is in the range of, let's say, 1, 5, 10 centimeters, the ripple length 20, 40 centimeters in that range, some distances between the ripples, and we did that for different discharges and different turbulent Schmidt numbers. So, and to show you some results of the reference case, first here a view on the mesh. So, and the height was here 5.6 centimeters, and you see that the mesh is quite fine. So the mesh resolution, so was in the range here. The edge sizes were, let's say, in the range of a few millimeters. So we have a quite fine mesh here in the water, and also up to the free water surface, and then of course we are more coarse in the air. So, and we see here flow from left to right, high flow velocity above the ripples, and of course smaller flow between the ripples. So why the flow is smaller between the ripples, we can see here. So of course here the flow over the ripples, and we see eddies that are occurring here. Yeah, and here is a case where a tracer has been injected, and the tracer is now transported from left to right. So it goes over the ripples, and then in a second, the scale here switches from 1 to 0.05. And we see now that we have some tracer is retained. We have seen the eddies, some tracer is retained here between the ripples. And it takes a bit longer until this tracer is also removed. Okay, so from the many cases, I have two where I want to show you some other results. So for example, if we double the ripple length, as shown here, then the system completely looks different. So while we had the eddy before, now with doubling the ripple length, no eddy does occur. So we have a very smooth flow here, as you can see. And of course, the tracer is removed much, much faster. So we also see here, we have a bit higher pressure on the upstream side where the water comes, and a bit lower pressure here around the crest. This lower pressure, what we also have seen in the Fehlmann experiment, where our simulations, where we have this drop down of the pressure, we also see it qualitatively here. And again, another case where we introduced a distance of 20 centimeters between the ripples, and what we see here, we also see an eddy structure. Of course, the eddy structure is now much, much larger. So, and we see a wider recirculation zone, much more tracer is retained here, but the residence time overall has been shorter. So the reviewers asked us to do some more investigations, and we did. So they wanted to know, for example, how is the pressure increase at the middle ripple for the different crazes? So the pressure difference, I've shown you an area where we have a high pressure. So we have a high pressure area and a low pressure area. And from that, we can determine a pressure difference along the ripple. So, and this pressure difference, let's say, is quite different in the different cases. So we see, for example, in case 3, it's relatively high. And we also considered the breakthrough curves. And for example, this high pressure difference was also related to a high peak in the breakthrough curve. Okay, we could draw some conclusions from that. So the solver was capable to simulate the complex flow fields between the ripples and the tracer transport between the ripples. And we found out that the discharges, the ripple size and the spacing significantly impact the flow and the retention behavior between the ripples. So in the next application case, and here I would like to give you some idea of the solvers for this case. They are similar in the other cases. So we have to choose solvers for the interface convection equation, for the pressure equation, and for the momentum equations. So, and maybe to comment on the pressure equation, this is a Laplace type equation. So we have symmetric systems of equations. We can use a PCG, precondition conjugate gradient method. We can use some algebraic multigrid preconditioning. So, and for the smoother in this multigrid cycle, we can use a Gauss-Seidel method. So for the momentum equation, the matrices are non-symmetric. We need a solver for non-symmetric matrices. One of them is BiCG, B-conjugate gradient method, and the preconditioning is carried out with some incomplete lower upper LU decomposition. Again, before we went to the ripple system, we checked the literature for some test cases, and we see here on the left where we have the flow through, let's say you can say through a rectangular domain or a rectangular dam. Imagine we have water standing here on the left, and then we have a porous medium, and then we have a seepage through the dam or through the domain. So, and the integral solver computed the green points, and the green points coincided quite good with other numerical and experimental results. And we had another case where the seepage line through a more natural or a more dam-like structure is investigated. And there is an analytical solution available after Casagrande, and again, the solver could reproduce this analytical solution quite well. So then we went back to the system of the first case, and we added the sediment. And we had two cases, one where where the sediment consists of sand with a diameter of 2 millimeters. The other case was with gravel, 50 millimeters, and the porosity was 25% in both cases. And then the same cases as before have been investigated. So, and we consider in the following the middle ripple. So, and what was important, we were interested, of course, what is the exchange between groundwater and surface water? So for that, we considered this ripple much in detail. So on the upstream side, there can occur areas with inflow and outflow. On the downstream side, there can be areas with inflow and outflow. So, and Tabea, let's say, computed all these fluxes to at the end have some ideas whether we have inflow or outflow Yeah, and to consider that in detail. And of course, these fluxes are quite important for other processes like biogeochemical things that do occur there in the hyporheic zone. So, and some results, let's start here to consider some results on the left. So we see here the ripple. So, and what we see here is, yeah, let's say, again, a very complex structure. So it's, again, the reference case. Maybe you have in mind from the previous simulation, we had one ripple area, one eddy. And now we have something like two eddies. We have one eddy here, another eddy here. And we see inflow from here associated with a bit higher pressure. And then we have, yeah, let's say, outflow here. So, and if the sand is replaced by gravel, again, we see that the results considerably differ. So let's have a look here. So we see for this case, the inflow and the through flow through the ripple is much more pronounced. The pressure is a bit higher here. So, and here we also have an eddy, but only one. Here we had two, and this is more, the through flow is much more important here. So the material, let's say, significantly influences the processes that do occur here. So we also looked to where do we have Darcy flow and where are we out of the range of Darcy flow. So for the second, we did that with checking the Reynolds numbers. So when the Reynolds numbers are smaller than 1, or let's say smaller than 10, then Darcy law is valid. But if it's larger than 10, let's say we leave the range of the Darcy law, of the validity of the Darcy law. So we see for the sand, higher Reynolds numbers around 5 to 10 only occur in a very thin part. So taking a groundwater model would, I think, still be fine. On the other hand, when we consider the gravel, so we see the non-Darcy area goes a couple of decimeters here, half a meter into the gravel. So, and what we also can, what happens is, of course, we have eddies here, and the eddies also go into the porous medium, and of course, the more we go down, of course, let's say the importance of the eddies is vanishing. So we could also draw some conclusions from that. So from the interfacial fluxes, we found out that small-scale structures and the kind of soil significantly influenced the magnitude. Sorry for going back, I forgot to give you the numbers. So the exchange flux here, 2.710 over -3 cubic meter per second and square meter, while here this is about an order of magnitude higher for the gravel. So with the one-way coupling, all these feedback effects cannot be taken into account, and the sediment properties influence also the surface water flow. So, and the non-Darcy flow areas occur below the interface, and how deep they go into the sediment depends on the permeability of the soil. That brought us to the next case, to include also the transport in porous inter. And again, or not again, so we were glad that we could collaborate with some researchers from Israel who have carried out experiments, and they are also co-authors of a publication. So they carried out experiments in a flume with ripples, and they introduced some traces we will see soon. So we got all the data from them with regard to the geometry, and later also with the concentrations. So, and what we investigated first was the flow. There we distinguished 3 different conditions. These conditions differed whether from the bottom we have, let's say, an inflow in the vertical direction. This is called gaining condition. Whether there is no in or outflow, this is called the neutral condition. And whether we have outflow, this is then called the losing condition. And we investigated these 3 conditions. And here first we see the results of the neutral conditions. So, and again, what we see here, we have an inflow area here. We have the through flow through the ripple. So, and let's say we could detect something like a flow cell here, and one large flow cell here, and another flow cell here, while here the direction is the other way around. So it enters from here and leaves here. Some pressure, higher pressure here, lower pressure here. Next case, the gaining conditions. So flow from the bottom enters the system, goes into the vertical, and of course this significantly influences the hydraulics here. So the flow cell is much more shifted to the top. So the flow cell becomes smaller. Again, here we see inflow and outflow here, but the other part is much more dominated from the boundary condition here. So from the inflow that leads in here to the outflow in the surface water system. That leads to lower pressures here and lower pressures here, and of course some higher pressures here. And last but not least, for the losing condition, so the water goes down, and again this has an impact on the hydraulics, on the flow cells. We have again one flow cell, or one pronounced flow cell here, another flow cell here. So in the previous case there was only one flow cell. Here we have two. Now again we have two. And the flow field, of course, is more influenced that the flow goes down here. So, and the pressure increase here was the highest, and the decrease also occurred here, and the pressure here was also smaller compared to the previous cases. Okay, so, and based on that, we did simulations with the tracer. So they are running over 60 minutes. So we see here the neutral conditions, on the top the simulations, on the bottom the experiments, and we see that they agreed quite well, visually agreed quite well. We see for the losing conditions, of course, the penetration of the tracer goes much deeper in the simulations and the experiments. And on the other hand, for the gaining conditions, there is less penetration in the simulations and also in the experiments. Yeah, so there are still a few seconds where you can enjoy this a bit. So, and after 60 minutes, it was stopped. Okay, and again, the reviewers wanted to have that not only visually, but they wanted to have some numbers. So, and Navier used some image processing tools to check which of the area is blue and which one is yellow. And from that, we could determine a root mean squared error between the experiment and the simulation. Unfortunately, this root mean squared error was computed over the whole time of the whole 1 hour, was relatively small. Okay, we could again draw some conclusions. So for the neutral, gaining and losing conditions, we overall could achieve good agreement between observations and numerical simulations. Okay, the last case, and this is a work that has been carried out by Veit Sobigolo, where we investigated a little bit another system, what was briefly mentioned in the beginning, a system that is built, or we will see quite soon, by chironomid, and this is something like an earthworm. And when this becomes a bit older, then it can fly. So, and why is this investigated? Because in lake sediments, many of these earthworms are found. And what they do is they dig a burrow, as shown here, and then they are here, something like here, or a bit more in detail, they are here, and they suck water from the one side and pump the same amount of water on the other side. So they need that water to survive, to get some oxygen and some food and so on. So, and we will see soon that by this pumping activities, let's say flow fields are induced, and these flow fields have a significant impact on the biogeochemical processes that do occur there. That has been found out by experiments and also other simulations. So, and the other simulations we will see soon were coupled simulations. So what you then have is a Darcy flow or a classical groundwater flow model here. You have a pipe flow model here. And of course, what you do, you start with a pipe flow simulation, assuming a rigid boundary. Then you get a pressure distribution. You give this pressure distribution to the groundwater flow model, but there is no feedback. So, and let's say the water column standing here is taken into account through boundary condition. This was a good opportunity for our solver to say, we don't have to couple models and take that into account by boundary condition. We can directly simulate the whole system with the same model concept. Okay, so, and what we see here are some results. We see results on the left for the integral solver, and we see on the right results of a coupled solver. So they qualitatively agree. So what we see here is the pressure, what I mentioned, this earthworm is sucking water from the left. So that leads to an under pressure here. And then the same amount of water is released on the other side, leading to an overpressure here. So the same qualitative result was simulated with the coupled approach. However, the numbers were roughly double as high as ours. So, and also, let's say this induces some flow fields. So what we see here, for example, through the suction here, of course, the flow goes to the pipe or to the burrow. And on the other side, through the pumping, the flow goes away from the pipe. But here in between, on the one hand, the flow is pumped out, leading to flow from right to left. And in addition here, there is the under pressure. So a strong flow from the right to the left is induced. So some flow activities are induced in the subsurface. And again, they have an impact on the transport of the transport and reactions of material that is occurring there. Yeah, I may add, we think nobody knows the exact truth, whether so they compute 6, the pressure difference of 6, we compute pressure difference of 3. Nobody really knows the truth, but we think that our approach is a bit closer to reality, because we could say here, this is something like a rigid system. So I have a fixed wall, I have a pressure distribution, I give from the pipe to the porous medium, no feedback effect occurs. Here, I would say I have more an elastic system. So there is this interaction, but some of the pressure also goes into the sediment, and that also leads to some other flow conditions within the pipe, so that we assume from the tendency that this might be more close to reality. And here are also some qualitative comparisons to experiments. So we have here our study, and we see here the sediment water interface, and here the burrow where it ends, and here the water is sucked. We have inflow here, and in experiments, let's say a qualitatively similar behavior was observed. And as also on the outflow side, we see here on the outflow side, our simulations look like this, while experiments found out a similar flow field. So let's say we can say qualitative agreement. That drove us to the conclusion that with the solver, we can do a simultaneous simulation of flow in the sediment, the burrow, and the water column. We got some plausible agreement of our solver with results of a coupled model and experiments. And what I mentioned, we assume that our model is a bit more close to reality. Yeah, that drives me to some general conclusions. So the 2 PhD students applied and extended an integral solver, focusing on the interaction between porous media and free flow. So I think we could obtain a couple of reliable results. while comparing this integral solver with experiments, analytical and other numerical solutions. So, and one advantage is that there are no empirical parameters that have to be adjusted. So, and our model conceptually takes into account feedback effects between the porous media and the free flow and vice versa. And it's also applicable in non-Darcy flow areas. So what I did not mention during the simulations, or only very briefly, but we have to mention, is that this solver is very, very expensive. So we have seen the systems that we investigated are quite small, a couple of meters, 10 meter, maybe 20 meter, and a meter high. We did 2D and 3D simulations, and the computational times, the meshes were around 10,000, 100,000 in one simulation, up to 1 million cells. It's not small, but also not that high. Several of the simulations on 100 cores take many days. So therefore, this is very, very expensive. Extremely high computational effort. So what I heard, you are investigating hydrological systems. So of course, this is not a good alternative for that. So let's have a look where this solver is, of course, interesting. It's interesting when we consider the area which is quite close to the interface. So urban water interfaces, we consider interface domains in that area. Of course, this is quite relevant. If we go down in the sediment or the groundwater, depending on the sediment, it's a very small layer, but also can go up to a couple of decimeters. But if we think about real groundwater systems, a couple of meters or even much, much more, then the difference is negligible. So it can also be interesting for some specific systems, as we have seen at the end with this burrow. What I also addressed a bit is it's quite suitable for flow through highly permeable soils or porous media. So what work is currently underway? So VIDE is doing a systematic comparison between the integral solver and the coupled model. And for the coupled model, he's on the one hand investigating the Navier-Stokes solver, but also a shallow water flow solver. So also there will be considerable differences whether we use shallow water flow or Navier-Stokes. The colleagues in Israel also did some experiments with heterogeneous sediments. He already did some simulations. So what could be done is to set up some upscaling methods. So you may know from those who are a bit more familiar with hydraulics, river hydraulics, when you have to assign a friction coefficient to a rippled riverbed, you can look into a table, and depending on the geometry of the ripples, you can give a friction coefficient. So, and I had in mind to formulate an exchange coefficient for water between surface water and groundwater, depending on the ripple geometry, possibly also on the discharge. So this in principle only means that to apply the solver we have in many, many cases and determine some relations. And what we are also planning, because the new PhD student, Finn, Illa knows him quite well. He educated him also to some extent. So he will start soon after he has finished his master's thesis. And there, most probably, we will look to systems, where the porous, where the flow velocities in the porous medium are a bit higher. For example, dikes. So if we have a dike, let's say on the one hand, we have the seepage through a dike. When we have overtopping of the dike, then in addition to the seepage, let's say we have the flow over the dike. On the outflow side, then at some time, we have also some outflow. When we want to do that with coupling several models, shallow water model or a wave model and an unsaturated model, that would be quite tricky. And with our model, we can do that with the same model concept. So in this, most probably we will investigate when the next PhD student will start. Okay, most of the, I showed you 4 cases for 4 applications, and all these 4 applications have been published. and further references here. And that's all I want to mention. Thank you for your attention, and I'm happy to answer any questions.
Thank you, Reinhard. That was great. We can take quickly some questions. So there is one question in the chat, but maybe you can just say this, Yongxiang.
Okay. Because in one figure I saw you mentioned there is a turbulence eddies near the dunes. So I was wondering, because you need to use the turbulence model in your code. So how does the turbulence model affect the eddy, and how does that further affect the pressure distribution?
Yeah, I did not fully get your question, but I may mention that, let's say for the turbulence, in some cases we used in the first application case, for example, the simulations were done with a large eddy simulation. In the other cases, we used K omega SST or K epsilon model. Does that answer your question?
Yeah, I think it partially answered my question. But one question is, if we use different turbulence model, because the turbulence model affects the distribution of the turbulence eddies, and
of
that
course
further affects the pressure distribution. I'm not sure if you use different turbulence model, how does the model affect the pressure distribution?
Yeah, of course it affects both. So let's say what the LES is the more complex model. So
yeah,
in some cases we found out when we take a bit simpler model like K epsilon or K omega SST that the differences were very, very small, and then we decided not to take LES but to take K epsilon or K omega. In the first case, we saw there were bigger differences, so therefore we did the simulations with LES. But again, the factor in the CPU time is factor 10.
Okay, thank you.
Any other question? Yeah, Boris, go ahead.
There is a question. This is Boris Fabishenko. So you took into account the resistance term for the interface between the free flow and porous media. And my question is whether you use several equations to describe the resistance. My question is whether you used the Brinkmann equation.
We have not used the Brinkmann equation. I introduced that in the in the state of the art. This is a two-domain approach, and what we are following is a single-domain approach. So we use the same model concept for the porous medium and for the free flow, and of course the porosity differs depending on whether we are in the free water or in the porous medium. So, and the resistance term, so I may show it again in one of the slides. So, okay, so we are here. So, and okay.
We can see.
I hope then you can see it.
Yeah,
We can.
So this is this D term where D, which includes two effects, and these effects have been determined by some experimental studies. First one is Mr. Ergun. He developed an approach how to take into account the friction between the fluid and the porous medium. And the second term was developed also based on experiments by a person called Van Gent to the increase of the effectiveness, and this takes into account recirculation effects in the porous medium. So we did not so we took these terms, or this porous interformulation as it was available, and let's say for material where the grain size diameter is bigger than a millimeter, we obtained good agreement, and it's even much better for when the diameter is bigger. Then this is the CPU times, let's say, also reduce a lot.
And so the system is characterized by low Reynolds numbers. Is that right?
These take into account these effects, of course, and these effects, the bigger the Reynolds numbers, the bigger this term probably is, because you see here, it depends on the velocity. Both terms depend on the velocity. The higher the velocity, the higher this, let's say, this resistance term.
Okay. Okay. Thank you.
You're welcome.
Thank you. We may take one more question, although we are over 9 minutes.
Professor Hinkelmann, can you hear me?
Yes.
Yeah, nice to see you. That's a great talk. I'm wondering, because in the results, you show the surface water simulation and you use two-phase flow, which means, in my opinion, the surface water can fluctuate. But in one of the conceptual figure in your methodology, you use a upper wall condition, which means the surface water is constrained within the wall. So I'm wondering if you have done any comparison between these different upper boundary conditions and if this difference affect the simulation of hybrid exchange.
Yeah, let's let me go to the slide again. So the upper wall, let's say, I have to mention that we did single phase and two phase flow simulations. And what we see here is a figure of a single phase flow where there was an upper wall. In the other cases we do have, let's say, we also have an upper boundary, but the system is, let's say, 50% filled with air and 50% filled with water. So, and the lower boundary, where we just had water flow, of course, it is closed here. And in the cases where we added the sediment, we could, the boundary, we could also close it. Then we had the neutral conditions, or we could give an inflow or an outflow describing this gaining or losing conditions. Let's say what you also investigated intensively in your PhD.
Okay, so would you say that makes difference to use single phase and two phase flow?
Let's say at the beginning, before we did two phase flow simulations, we also made single phase simulations to compare numerical results with other results for the different turbulence models and so on. I have not told that here. I have these slides also here. The two-phase flow approach is then necessary for the water level, or let's say for two cases. First, when we have this rippled system, so we also have some variation of the surface. So, and if you have a single phase flow approach, then you have a rigid boundary on the top, and then you don't have this, let's say this movement of the surface. So, and this is also related to has also some impact on the eddies between the ripples. So therefore, the smaller the water depths, the more pronounced is this, the necessity to use a two-phase flow approach.
Yes, thanks.
And including the non-hydrostatic pressure distribution. It would have been interesting also to compare our results with yours, maybe there is any opportunity in the future.
Yeah, sure, of
Yeah.
course.
Hmm?
Happy to.
Hmm?
Great. So that brings to the conclusion of this talk. So unless like if there is any burning question, we may thank Reinhard and we'll interact with him in the future. Thank you. That was a very good talk. And do you have any?
No, I was just going to say very great talk. We really appreciate it. Learned a lot. Thank you.
Thank you.
Yeah, thanks. It was a pleasure if it has been interesting for you. So I can imagine, yeah, what I heard from Ilan, from your daily life, you are investigating much larger systems. Yeah, what of course is also very interesting consider surface water, groundwater interactions on the catchment scale. Of course, very interesting.
Thank you. Good night, Dr. Hinkelmann. I know it is late there in Germany.
Yeah, it starts to get a bit dark, but yeah. So please enjoy your afternoon and your lunch soon.
Sure. Thank you. Bye.